This is continuing the Allocator Designs section of Philipp Oppermann's blog. The description, or a link to the blog is in the description. And we will we did bump allocator in the previous video. And now we're working on linked list allocator, and then the next one will be the fixed size block allocator. So let's dive right in. Linked list allocator. A common trick to keep track of an arbitrary number of free memory areas when implementing allocators is to use these areas itself as backing storage. This utilizes the fact that the regions are still mapped to a virtual address and backed by a physical frame, but the stored information is not needed anymore. By storing the information about the freed region in the region itself, we can keep track of an unbounded number of freed regions without needing additional memory. The most common implementation approach is to construct a single linked list in the freed memory, with each node being a freed memory region. Right, so at the start of the heap, we have the unused head points to the first unused block, and then the linked list will point to each next unused block. Each list node contains two fields: the size of the memory region and a pointer to the next unused memory region. With this approach, we only need a pointer to the first unused region, called head, to keep track of all unused region, independent of their number. The resulting data structure is often called a free list. As you might guess from the name, this is the technique that the linked list allocator crate uses. Allocators that use this technique are also often called pool allocators. Implementation. In the following, we will create our own simple linked list allocator type that uses the above approach for keeping track of free memory regions. This part of the post isn't required for future posts, so you can skip the implementation details if you like. I guess that warning should also have been in the bump allocator, because we're going to take that out. But we're gonna keep them all, because that's the way I roll here. So we have pubmod bump, and we're going to have pubmod linked list. And then we're going to create a new file called, let's save this, and it should fail, right? And then allocator/linked list. Struct list node size, usize, and next is an option static. I'm just thinking now, this needs to fit inside the allocated region. So that means the minimum allocation size has to be able to fit this whole thing. So if somebody asks for 1 byte of allocation, you still need to allocate enough to fit a list node, right? Let's see if they get into that. Like in the graphic, a list node has a size field and an optional pointer to the next node, represented by option tick static mute list node type. The tick static mute type is semantically describes an owned object behind a pointer. Basically, it's a box without a destructor that frees the object at the end of the scope. So here's our implementation of a list node. We have a const function new. I'm guessing it's const because we're going to use it in a static variable. Self. Wow, I can't type it. Self. There we go. List node. Size next. None. And we have a start address. And then we have an excuse me, end address, usize, self start adder plus self size. Okay. So each list node is going to keep track of where it starts and ends. The type has a simple constructor function named new and methods to calculate the start and end addresses of the represented region. We make the new function a const function, which will be required later when constructing a static linked list allocator. Note that any use of mutable references in const functions, including setting the next field to none, is still unstable. Okay. In order to get it to compile, we need to add a feature const mute refs to the beginning of our lib.rs. Is that still true? Nope. First I have to get all the typos out of the way. Okay, mutable references are not allowed in constant functions. Right, so this is the mutable reference. So we need to add the feature to the beginning of lib.rs. Okay, so go to lib, and we're going to pull in this new feature. Okay, now it compiled. We have warnings, but that's because we're not using anything, right? With the list node struct as a building block, we can now create the linked list allocator struct. So let's put this at the top here, pub struct linked list allocator. Head of a list node. And we're going to have the const function new, self, head, list, node, new of 0. So the first size is going to be 0. Okay. And then we're going to have an unsafe init. Self add free region. Okay, and then add free region. Not pub. And it's to do. Okay, so does this check? It does. The struct contains a head node that points to the first heap region. We are only interested in the value of the next pointer, so we set the size to 0 in the list node new function. Yeah, so I guess we start out with a 0 size, and then we're going to add a free region for it. Making a head a list node instead of just a tick static mute list node has the advantage that the implementation of the alloc method will be simpler. Okay. Like for the bump allocator, the new function doesn't initialize the allocator with the heap bounds. In addition to maintaining API compatibility, the reason is that the initialization routine requires to write a node to the heap memory, which can only happen at runtime. The new function, however, needs to be a const function that can be evaluated at compile time because it will be used for initializing the allocator static. For this reason, we again provide a separate non-constant init method. Okay. That all makes sense. The init method uses an add free region method, whose implementation will be shown in a moment. For now, we use the to-do macro to provide a placeholder implementation that always panics. Okay. The add free region method. This seems like it could be cleaned up a little bit, but Christopher Davis, thank you for the follow. The add free region method provides the fundamental push operation on the linked list. We currently only call this method from init, but it will also be the central method in our dealloc implementation. Remember, the dealloc method is called when allocated memory region is freed again. To keep track of this freed memory region, we want to push it to the linked list. The implementation of the add free region method looks like this. All right, so we're going to have a super line up. Oop, forgot the use. And use core mem. Okay, so in our linked list allocator, we're going to create a new, and we're going to implement, apologies for the train in the background there, assert eq, line up, header, mem, a line of list node. Okay, so this is something built into Rust. It tells us the alignment of whatever the list node type is. Assert bang size is greater than or equal to mem size of list node. Okay. A couple of quick asserts, and then let mute node equals list node. New size. Node next is self head next take. Self head next take. So this is so take on an option. What does that do? I'm not familiar with that. Or does that just copy it? Is that like cloning it or something? Node pointer equals adder as star mute list node. Node pointer, right node. And then self head next is equal to sum mute node pointer. Oh, Teravassal. However you pronounce it. Apologies for butchering it like that, but thank you very much for the follow. Much appreciated. Okay, so and then we're leaving off the semicolon. So this assignment must be assigning and returning, right? Self-head next is still an option. Oh, no, we're not returning it. This is just a missing semicolon. Okay, that makes more sense. I didn't think Rust equal assignment operator returned something. The method takes a memory region represented by an address and a size as an argument, and it adds it to the front of the list. Right. First, it ensures that the given region has the necessary size and alignment for storing a list node. Then it creates a node and inserts it to the list through the following steps. Right, so it's asserting that the region is going to be big enough. So that means whenever we return a free region, we're going to have to make it a minimum of this size. And then it creates a node and inserts it to the list through the following steps. Right, so this is just basic linked list work. So we create the node. We take the nodes next. We set the nodes next to the current heads next. We calculate the node pointer as an address, the address that we're returning, and setting it to a list node. We've already determined that it's aligned correctly, so we should be able to do that. We write that through the node pointer and then set the head next to the new pointer. Yeah, so this is basic linked list. Step 0 shows the state of the heap before the add free region is called. In step 1, the method is called with the memory region marked as freed in the graphic. This blue section here. After the initial checks, the method creates a new node on its stack, the size of the freed region. Then it uses the option take method to set the next pointer of the node to the current head pointer, thereby resetting the head pointer to none. Oh, I see. Okay, so what take does is it swaps it out. Let's see. Rust option type. Takes a value out of the option, leaving a none in its place. So that means it's, yeah, so it's mutable here. So that's why we can do that. Okay. That's something. So I just learned something. That's good. In step 2, the method writes the newly created node to the beginning of freed memory, of the freed memory region through the write method here. Then it prints the head pointer. Then it points the head pointer to the new node. The resulting pointer structure looks a bit chaotic because the freed region is always inserted at the beginning of the list. But if we follow the pointers, we can see that each free region is still reachable from the head pointer. Yeah, so it bounces around. It's not going to be in sorted order based on memory address, because that wouldn't make any sense to do, because it's more work and it would achieve the same exact thing. This is all O of 1, so it makes it nice and speedy. Okay, the find region method. The second fundamental operation on a linked list is finding an entry and removing it from the list. This is the central operation needed for implementing the alloc method. We implement the operation as a find region method in the following way. Okay, so over here we'll say find region. Returns an option tuple. Okay, static mute list node and usize. That just fits, so it'll probably get wrapped. Let mod current equals mute self head, while let sum ref mute region equals current next. If let okay alloc start is equal to self alloc from region size align. Okay, so we're going to have to write this alloc from region function. That's new. Let next is region next take. Let ret equals sum current next take unwrap alloc start. So this is assuming that there is a current next, right? Current next is equal to next and then return ret. Else current is equal to current next as mute unwrap. And if that all fails, we return none, saying there's no memory. Huh. Okay, so this doesn't exist, but I think everything else worked, right? We only have one error. Yep. Okay. And it didn't wrap this for whatever reason. All right. The method uses a current variable and a while let loop to iterate over the list elements. Sure. At the beginning, the current is set to a dummy head node. On each iteration is then updated to the next field of the current node in the else block. Oh, here. Okay. If we can't alloc from the region, then we go to the next one. That makes sense. If the region is suitable for an allocation with the given size and alignment, the region is removed from the list and returned together with the alloc start address. When the current next pointer becomes none, right? If alloc from region returns so this is a results type, right? If this returns an error, then we return none. Here, if this becomes none, got it. If this becomes none, then loop exits. This means that we iterated over the whole list but found no region that is suitable for an allocation. In this case, we return none. The check whether a region is suitable is done by alloc from region function, whose implementation will be shown in a moment. Let's take a more detailed look at how a suitable region is removed from the list. Step 0 shows the situation before any pointer adjustments. So we happen to have a situation where everything's in order here. The region and current regions and region next and current next pointers are marked in the graphic. Okay. In step 1, both the region next and current next pointers are reset to none. By using the option take method, the original pointers are stored in local variables called next and ret. Here and here. In step 2, the current next pointer is set to the local next pointer, which is the original region next pointer, right? And the effect is that current now directly points to the region after region. So that region is no longer an element of the linked list. Right? So we have head to current, and then current hops over the region that we just wanted to allocate from and points to the next freed region. And ret points to that one. On the alloc from region function. The alloc from region function returns whether a region is suitable for an allocation with given size and alignment. It's defined like this. Okay. and this returns a result, right, of usize or a unit error. That's fine. Here's where we're calling a line up with the alignment given. Alloc end is equal to alloc start, checked add, size, OK, or unit. So this unit is actually the error here. I'm just going to return an error. I don't know why this just couldn't be an option then. Right? This should have been able to be an option. But it does save a little checking here. If alloc end is greater than region and adder, return error. Let excess size is region and adder as alloc end. Excess size is greater than 0 and excess size is less than mem size of list node, return error. Right, so if we can't fit a list node in the excess region, then we can't allocate because we wouldn't be able to reclaim, we'd have a memory leak. We wouldn't be able to reclaim that memory. Otherwise, return alloc start. We'd have to wait for this region to grow. So when we free something, we haven't done that yet, but when we free from region, we're going to have to link up things that are contiguous. We have add free region, which doesn't do that. But maybe we'll get to that. First, the function calculates the start and end address of a potential allocation using the align-up function we defined earlier and the checked add method. If overflow occurs, or if the end address is behind the end address of the region, the allocation doesn't fit in the region and we return an error. The function performs a less obvious check after that. This check is necessary because most of the time an allocation does not fit a suitable region perfectly, so that part of the region remains usable after the allocation. This part of the region excuse me, must store its own list node after allocation. So it must be large enough to do so. The check verifies exactly that. Either the allocation fits perfectly, excess size is equal to 0, or the excess size is large enough to store a list node. Okay, implementing global alloc. With the fundamental operations provided by the add free region and find region methods, we can now finally implement the global alloc trait. As with the bump allocator, we don't implement the trait directly for the linked list allocator, but only for the wrapped locked linked list allocator. The locked wrapper adds interior mutability through a spin lock, which allows us to modify the allocator instance, even though the alloc and dealloc methods only take self-references. Yeah, that was the same from the previous video. Okay, so list build, it will not, because I typoed this. There we go. We have 6 warnings now because, again, we're not using this yet. We're going to use super locked. And a lineup, we're going to use our global alloc and layout. And we're going to need core pointer as well as core mem. Right? And now we have more warnings because we're not using those yet. Okay, so now we're going to implement global alloc for this guy. Let's put it right here at the top. Unsafe impl global alloc for locked linked list allocator. Unsafe function alloc. Returns immutable reference to a U8. Ooh, this doesn't exist yet. Size align. Yeah, okay. So we're going to have to write that as well. Let my allocator equals self lock. Okay, so now we've locked it. So we find a region. If we found a region, alloc end is equal to alloc start, checked add, size, expect, overflow. Okay. This shouldn't happen, right? Because we've already checked, we shouldn't be able to allocate the region without it fitting. Right. And it should, if we have an excess size, then we should be able to fit the list node in it, because we wouldn't return, find region wouldn't return a region with an excess size that doesn't have enough room. Else pointer null. Okay. Missing a dealloc implementation, right? Okay, so let's do that. Unsafe fun dealloc. Let size and nothing is equal to list linked list allocator. Size align. Layout. Self lock. Add free region. Pointer as usize and size. Right. That's all we need to do there. Right. And we just don't have size align yet. Let's start with the Dialect method because it's simpler. First, it performs some layout adjustments, which we'll get to, which we will explain in a moment, and retrieves a mutable linked list allocator reference by calling the mutex lock function on the locked wrapper. Then it calls the add free region function to add the deallocated region to the free list. The alloc method is a bit more complex. It starts with the same layout adjustments and also calls the mutex lock. Mutex lock function to receive a mutable allocator reference. Then it uses the find region method to find a suitable memory region for the allocation and remove it from the list. If this doesn't succeed and none is returned, it returns a null mute to signal an error as there is no suitable memory region. In the success case, the find region method returns a tuple of the suitable region, no longer in the list, and the start address of the allocation. Using alloc start, the allocation size, and the end address of the region, it calculates the end address of the allocation and the excess size again. If the excess size is not null, it calls add free region to add the excess size of the memory region back to the free list. Finally, it returns the alloc start address cast as a star mute U8 pointer. Layout adjustments. So what are these layout adjustments that we do at the beginning of both alloc and dealloc? They ensure that each allocated block is capable of storing a list node. This is important because the memory block is going to be deallocated at some point where we want to write a list node to it. If the block is smaller than a list node or does not have the correct alignment, undefined behavior can occur. The layout adjustments are performed by a size align function, which is defined like this. Okay, so let's add that here. And then pad to align. Let size is equal to layout. Size max mem. Size and layout align. So that's interesting. We pad to align on it and then we realign it here. Okay. First, the function uses the align to method on the passed layout to increase the alignment to the alignment of a list node if necessary. It then uses the pad to align method to round up the size to a multiple of the alignment to ensure that the start address of the next memory block will have the correct alignment for storing a list node 2. That makes sense, right? In the second step, it uses the max method to enforce a minimum allocation size of list node. This way, the dalloc function can safely write a list node to the freed memory block. All right, using it, we can now update the allocator static in the allocator module to use our new linked list allocator. So instead of the bump allocator, we're going to use a linked list allocator. And we're going to change that here. Linked list. Right? And it builds. Since the init function behaves the same for the bump and linked list allocators, we don't need to modify the init call in init heap. When we now run our heap allocation tests again, we see that all tests pass now. Well, let's hope so. Let's see what happens if I try to run them. Yeah, look at that. This shows that our linked list allocator is able to reuse freed memory for subsequent allocations. In contrast to the bump allocator, the linked list allocator is much more suitable as a general purpose allocator, mainly because it's able to directly reuse freed memory. However, it also has some drawbacks. Some of them are only caused by our basic implementation, but there are also fundamental drawbacks of the allocator design itself. Merging freed blocks, right. The main problem of our implementation is that it only splits the heap into smaller blocks, but never merges them back together. Consider this example. In the first line, excuse me. In the first line, 3 allocations are created on the heap. 2 of them are freed again in line 2, and the third is freed on line 3. Now the complete heap is unused again, but it's still split into 4 individual blocks, right? At this point, a large allocation might not be possible anymore because none of the 4 blocks is large enough. Over time, the process continues and the heap is split into smaller and smaller blocks. At some point, the heap is so fragmented that even normal-sized allocations will fail. To fix this problem, we need to merge adjacent freed blocks back together. For the above example, this would mean the following. Like before, 2 of the 3 allocations are freed on line 2. Instead of keeping the fragmented heap, we now perform an additional step in line 2A to merge the 2 rightmost blocks back together. In line 3, the third allocation is freed, like before, resulting in a completely unused heap represented by 3 different distinct blocks. In an additional merging step in line 3A, we then merge the 3 adjacent blocks back together. The linked list allocator crate implements this merging strategy in the following way. Instead of inserting freed memory blocks at the beginning of the linked list on a deallocate, it always keeps the list sorted by start address. This way, merging can be performed directly on the deallocate call by examining the addresses and sizes of the 2 neighbor blocks on the list. Of course, the deallocation operation is slower this way, but it prevents heap fragmentation we saw above. Performance. As we learned above, the bump allocator is extremely fast and can be optimized to just a few assembly operations. The linked list allocator performs much worse in this category. The problem is that an allocation request might need to traverse the complete linked list until it finds a suitable block, right? Since the list length depends on the number of unused memory blocks, the performance can vary extremely for different programs. A program that only creates a couple of allocations will experience a relatively fast allocation performance. For a program that fragments the heap with many allocations, however, the allocation performance will be very bad because the linked list will be very long and mostly contain very small blocks. It's worth noting that this performance issue isn't a problem caused by our basic implementation, but a fundamental problem of linked list approach. Since allocation performance can be very important for kernel-level code, we explore a third allocator design in the following that trades improved performance for reduced memory utilization. I guess the other thing to be able to do is to sort the list based on size of block. It makes it harder to do the merging, right? Because the merging is simplified by the fact that we sort it by memory address. But you can also sort by block size and then have multiple pointers into the linked list for different block size start regions or something. I don't know. Maybe that's getting overly complicated. Okay, but this is working. Git status, git add source, git commit -m, a basic linked list allocator implementation without free block merging. All right. That is going to wrap up my stream for today.